It should be about the time to start our lesson. We have already started in the discussion of the lecture notes set number 4, which is concerned with the thermodynamics. And at the very beginning, we talk about various fundamental concepts that is relevant to our discussions. In particular, we talk about the thermometers, various types of properties that are dependent on temperature could be used for measurement, well, could be used for the as a thermometer. Of course, there are always limitations. For example, liquid in glass tube thermometers like the mercury thermometer or the alcohol thermometer, they have the problem when the temperature goes below the freezing point of the liquid. And a very versatile type of a thermometer is the constant volume gas thermometer, which relies on the property that the constant volume of gas has the temperature that is dependent on the pressure. So that would relate to an important topic in the discussion of thermodynamics, and that is the ideal gas law, which is mentioned in the later part of the chapter 19. And of course, we also mentioned about the absolute temperature scale. That is reliant on the fact that in the case of the ideal gas, assuming that the gas does not freeze into liquid or solids, it would extrapolate to zero pressure at a fixed temperature value of minus 270.15 degrees Celsius, which we define it as the 0 Kelvin, which is the absolute zero, the lowest possible temperature that we could achieve. That is actually true no matter it is in the laboratory or in the universe. The absolute zero is the minimum temperature that could be achieved. No lower temperature can be observed so far. So we also talk about some phenomena that is related to the temperature, and that is the thermal expansion. No matter it's solid, liquid, or gases, you would have expansion of the material with the increasing temperature. Depending on whether you are measuring it in 1 dimension, 2 dimension, or 3 dimension, you would have the linear expansion coefficient, volume expansion coefficient, or the area expansion coefficient. As a matter of fact, for most of the cases, the 3 values are actually related, at least in the first approximation. Area expansion coefficient is about twice the linear expansion coefficient. And for solids, the volume expansion coefficient is about 3 times the linear expansion coefficient, which can be deduced by simple consideration of the expansion of a solid in all the 3 dimensions. Okay, and we at the end of the last lesson, we talk about the ideal gas law, which is one special case of the equation of states. The equation of states describes the macroscopic behavior of the material. And in particular, we talk about the case of the gas, which for low pressure or low density gases far away from the boiling point, it could be described by the ideal gas law. In the ideal gas law, you have a very simple relation among the parameters P, V, and T, and correspond to the number of moles of molecules. So instead of counting molecules one by one, we count them in terms of moles, which one mole of molecule is equal to one Avogadro's number of molecules. Avogadro's number, you could refer it to the notes, is around 6.02 times 10 to the power 23, which is a very large number. And R is the universal gas constant. Right. So for today, we would march into the next chapter, which is the first law of thermodynamics. That is a very grand name, but if you consider it in the other way around, it is just the conservation of energy. So at the beginning, we would talk about some concepts that would be used in the equation for conservation of energy, because when we mention about the energy conservation, it implies that we have various forms of energies. In fact, that is one of the big hurdles, one of the big barriers at the beginning of the thermodynamics. At the beginning, people did not recognize the connection between the thermodynamics and mechanics. As I said, thermodynamics refers the connection between the macroscopic behavior of, say, the gas, such as pressure, volume, and temperature, to microscopic behavior, such as the motion of the particles. And in fact, it was left until mid-1800, people have found that the two concepts, mechanics and thermodynamics, are related to one another. And that is by a experiment that shows the equivalence of the heat energy and the mechanical work done. So we have to connect the various types of energies together: work done, heat energy, as well as what we call the internal energy of a system. So the general idea of the first law is to connect these parameters together. So at the beginning, we would mention what these parameters are actually. For the ordered system of atoms, no matter they are liquid, solid, or gases, they would possess some energy. Well, that is a belief, if you like, in a certain sense. But we could justify our belief or our argument by considering what happens to the atoms or molecules in a system of particles, in a system of atoms. So the internal energy is actually the sum of all the energies associated with its microscopic components, which, if you like, is just the atoms or molecules. And the big question is, how do we consider the internal energy? The idea is that all energy, if you consider it for the internal energy, in order to calculate it, that would actually be a very painful process. Say, in the simplest case of the collection of atoms, let's consider the case of the gas. In the gas molecules, you would have, well, in the atomic model, we would consider them to be fast-moving particles bouncing from one wall to the other. They are normally not interacting with one another unless they have collisions. So at least we could assign some energies to them, and that is the kinetic energy of the molecules or the atoms. That would be counted towards the internal energy. On the other hand, the linear kinetic energy does not represent the whole story. In fact, in the case of the gas molecules, if you have not single atoms, but two atoms in a molecule, you would have other forms of energies. Of course, the center of mass could be moving in a linear way, so you have a translational kinetic energy, or if you like, linear kinetic energy that can be calculated by 1/2 mv squared. On the other hand, because you have a center of mass and you have the atoms distributed around the center of mass, they could actually rotate. So there would be a rotational kinetic energy. And to make it even more complicated, sometimes the particles could vibrate. And therefore, there would be vibrational kinetic energy, just like the case of a spring and mass system. So this would actually make the things fairly complicated. In our consideration, we would mostly be concerned with the translational kinetic energy. And actually, if we want to include all the possible forms of energies, we may have to include interactions between molecules, and that would become the potential energy between molecules. As I said, interaction between gas molecules would be negligible, but they are definitely present in the case of liquids and solids. And that is why consideration of the internal energies would be kind of hopeless in the case of liquids and solids. The interaction is not simple at all. So for the simplest case, we would start with the gas molecules that are independent of one another. And that would be one of the topics we discuss later in the lecture notes. So that is the main idea of the internal energy, referring to the energy possessed by all the atoms or molecules, if you like. And another form of energy that is always present in the system, or if you like, that is present between the system and the surrounding, is the heat energy. Now, heat energy is something different from the internal energy. For internal energy, it is present within the system. So let me try to redraw it. For the internal energy, you have a system. The internal energy, you are considering the energy possessed by the particles within the system. We don't care what is outside. On the other hand, for the heat energy, you cannot consider only the system itself. You have to consider the boundary between the system and the surrounding. So there is a boundary between the system and the surrounding. Sorry for the poor handwriting. Surrounding. Now, what is heat? According to the definition of the thermodynamics, it refers to the movement of energy. It refers to the transfer of energy due to a temperature difference between the system and its surrounding. Internal energy exists by itself within the system. Heat, on the other hand, is the type of energy that could only occur when there is a system and a surrounding, and there is a temperature difference between them. So this would be something very precise. In the case of physics, the two terms are different. And actually, people in the daily life, they would also mix up with another term, temperature. So let us make it straight in the physical sense. You have the system and the surrounding. Inside the system, molecules are moving around or having interactions with each other. This would create, or this would correspond to the internal energy of the system itself. And of course, due to the presence of the energy, internal energy of the system, it has a temperature. It has a boundary that is in contact with its surrounding. So the difference in temperature between the system and the surrounding would give rise to a non-equilibrium condition, a non-equilibrium in terms of a thermal situation. So there would be a heat that occurs, the flow of heat energy that occurs between the system and the surrounding. Of course, if you have the system at a higher temperature than surrounding, heat energy flows from the system to the surrounding and vice versa. So there are two terms already, internal energy and heat. Now, what about the unit of the heat? We mentioned that it is energy. So the SI unit is joule, but in the textbook or in many of the descriptions, another commonly used energy unit is the calorie. It refers to the amount of heat energy required to raise the temperature of 1 gram of water from, by 1 degree Celsius. So that is another commonly used unit. Of course, the actual amount of energy conversion between joule and calories, for those of you who remember the numbers well, 1 calorie is around 4.18 joule. So you do not need to remember the numbers. It will always be given in the test or in the examination, but that is just for your reference. It refers to the heat energy required to bring the temperature of 1 gram of water to be changed by 1 degree Celsius. That is an old unit, but it is still commonly used these days. And finally, we have the other type of energy, that is the work done. And the work done, of course, is a mechanical form of energy, which at the beginning, it does not seem obvious why the work done is related to heat in any case. But Joe has performed this experiment to show that the two forms of energy are equivalent to one another. He just made use of the mechanical work done performed by this particular machine. When the mass drops in the system, it performs the work by paddling in the water. Now it looks very funny, but during the process, the work done would be sufficient to raise the temperature of the water. So in this way, the effect would be identical to putting a fire next to the container and transfer the heat energy by the temperature difference. So in this experiment, he has demonstrated the equivalence between the work done and the heat energy. So that is the historical development. And this would be the definition, the mechanical equivalence of heat. And it is mentioned at here just mainly for your interest. So we have established in various ways the types of energy that may be present in the system or that may be added to the system. So let us try to take a look at an example and see how they could be converted into from one form into another. Here, you have a student who just had a big buffet and had a lot of calories consumed. He would like to take away all these intake energy by performing the equivalent amount of work done, which is in the form of lifting a barbell 50 kilograms in mass. So lifting the barbell once would consume a certain amount of work done. So in order to consume the 22,000 calories of energy, he has to raise the barbell for a certain number of times. And we are now trying to see how long or how many times it takes for him to raise the barbell. We assume at here that the internal energy change is equal to the work done. The work done for each raising of the barbell is equal to mgh, assuming that the boy does not regain any energy when he lowers the barbell. Well, for example, he just drops it, and so therefore he's not regaining any of the energy. He's not retrieving any of the energy. So mgh, m is the mass, g is the acceleration due to gravity, h. Here we assume this is a very tall boy raising a barbell by 2 meters. And altogether, he has to do it by n times in order to consume all the 2,000 calories of energy. So here is the calculation. Total work done, it is equal to nmgh, considering the total amount of energy to be consumed is 2,000 calories. So it's, let me see, 1 calorie is 4.186 joule, and 2,000 of them. So at the end, it would be around 9,000 times, or 8,500 times of the lifting. I have said that you do not have to remember the numbers. So you can see that it is around 8,500 times. If you take 5 seconds to do a lifting, which is already something very impressive, even with such a fast lifting, it takes him 12 hours to consume all the energy. So that doesn't sound to be a very useful strategy or very plausible strategy to mention it in this way. So that is how we could convert the energy from one form into another. And when we are putting energy in the form of heat to a system, when we put heat to a system, a very obvious effect to the system is that its temperature could be raised. Well, it is something quite easy to visualize even in our daily lives. You put a water kettle on the stove and you put it on fire. Due to the temperature difference, you will have the heat that is transferred. And the effect, of course, is that the water in the kettle start to boil. So there is a temperature increase. And how much heat energy is required to raise the temperature of a substance by 1 degree Celsius? It is something that we refer as the heat capacity. So the heat capacity refers to the amount of energy needed to raise the temperature of a system or a sample by 1 degree Celsius. So this would refer to any sample. As long as you are raising the temperature by 1 degree Celsius, the amount of energy required is the heat capacity. Now, of course, you have a boy that is holding a water kettle with 1 kilogram of water. The other girl is holding a water kettle holding 500 grams of water. The amount of heat energy required certainly would be different, even you try to raise both water kettles by 1 degree C. So do we have a more general way to describe the heating capacity? Well, the answer, of course, is yes. And that is something we call the specific heat. The idea of the specific heat is you try to quantify the amount of heat energy required to raise the temperature of your system by 1 degree C for each kilogram of the system. So instead of just trying to observe a particular system and raise the temperature by 1 degree C, you divide the system by its own mass. So you divide the heat energy not just by the temperature change, but also by the mass. In this way, you could have a quantity called a specific heat. And this specific heat allows you to calculate the heat energy required for any sample. For any sample that has a mass m, and you're trying to change the temperature by delta T. So that is the idea of the specific heat. In the form of the equation, this is the equation. Now, confusion always arises when you have various symbols. M is the mass, delta T is the change in temperature, C at here is the specific heat, Q at here is the heat energy involved in the process. So once again, same symbol appears in different contexts. C at here is the specific heat. So do not get mixed up with other physical quantities that appears earlier in the lecture notes. Here, it refers to the specific heat. And of course, the larger the specific heat of a substance, the more energy that is required for you to raise a certain mass of it by a certain temperature. So if you have a fixed value of m and delta T, if you have a fixed M and delta T, a larger value of C means a larger value of Q. So you need to put in more energy, more heat in order to raise its temperature by the same amount. So this is the equation. And just a summary on the sign convention. If you have a temperature increase, always remember delta T or any change, it is the final minus the initial value. The change in temperature, if the temperature is actually increased, delta T is increased, so would be the Q. And something you would also notice later, if there is energy transfer into the system, the temperature is increased. So that is something easy to understand. When you heat up the water, the temperature will increase, and there would be a transfer of energy into the system. And similarly, when the temperature of the system drops, you expect the energy of the system is removed from it. Therefore, Q and delta T are negative. So at here, let me see, I try to be consistent in my discussion. So you will see that heat has the symbol of Q. So far, that is what we see. And work done would have a symbol of W. Later, we would also have a symbol for the internal energy, and that is generally written in this way. So that is the internal energy. Typically, when we use the first law of thermodynamics, we do not consider the whole amount of internal energy. We usually just consider the change of internal energy. So that would be delta E INT. Well, that is a just a first introduction of the three important terms, and we would use these symbols fairly consistently during our discussion. So Q refers to the heat, W is the work done, and delta E refers to the change in the internal energy. This table provide you with a quick summary on the specific heat of various types of substance or materials. In general, metals are having relatively small specific heat, and liquids, well, depends on the type of liquid. Sometimes they have a very low specific heat, like in the mercury, which is a very good conductor of electricity as well as heat. But some of the liquid, such as water, it has a relatively high specific heat. So this is just a table for introduction. And the most important value of the specific heat, of course, is the specific heat of water. And it is quite high among many of the common materials. And this large value of the specific heat can be used to explain a lot of important phenomena in our daily lives. For example, why the area next to the sea would have a smaller temperature change compared with the inland area. The land area has typically a smaller specific heat compared with water. So water does not absorb the heat energy or release heat energy that easily compared with the land. Therefore, temperature difference in the daytime and the nighttime for regions next to the sea would be smaller compared with the inland area. So that is related to the high specific heat of the seawater, if you like, compared with the land mass. And a very important consideration for the heat energy transfer between the system and the surrounding is the calorimetry. And this is a technique used for measuring the specific heat of certain materials. The idea is like this. You have a certain material, for example, a block of iron. If you want to know the specific heat of the iron, you first try to measure the temperature of the iron. And of course, you have to know the mass of the iron as well. And then you drop it into a certain container of that contains some water. At a particular temperature. When the iron is dropped into the water, heat energy flows between the water and the iron if there is a temperature difference between them. Assuming no energy loss to the surrounding, well, that is a very common expression used in the calorimetry. Assuming no energy loss to the surrounding, you have only the heat energy transfer between the iron and the water. And so in this way, if we know the specific heat of water, and by measuring the temperature change of the iron before and after putting into the water, then we could calculate what is the specific heat of the particular material, say in this case, the iron. So the equation that is written can be shown below. Q cold corresponds to the heat energy gained by the cold system, a cold part of the system. For example, if the water is cold at the beginning and you have the hot iron drop into it, the Q cold will correspond to the heat energy gained by the water. And a minus Q hot refers to the heat energy lost by the hot part of the system. The minus sign just try to balance the sign of the two sides of the equation. Because if you have a hot system, when it loses energy, Q is a negative value. So you put a negative sign to balance the two sides of the equation. Well, of course, that is the expression form. But in terms of the actual operation, this would be something more practical. So here, we list all the parameters required for the calorimetry. You have a hot system, a hot part of the system or hot sample that is dropped into the cold water. Initial temperatures are shown as in the diagram. Of course, when you put the hot sample into the cold water, eventually they would achieve the same final temperature, TF. And from that, you could write down the equation for the transfer of heat energy from one side to the other. For the cold side, the heat energy gained is MWCW TF minus TW. The hot side, on the other hand, has Mx, Cx, Tf minus Tx. Remember, Tf should be lower than Tx because you have the Tx referring to the temperature of the hot sample. So Tf should be smaller than Tx. The term in the bracket is negative. Therefore, the negative sign in the front balances the two sides of the equation. So in this way, we could solve for the specific heat of the system. So this one is just a demonstration of the equation. Not sure if you have learned all this. So just a quick explanation. Left-hand side corresponds to the energy gained by the water, and the right-hand side, without the minus sign, it refers to the heat energy lost by the hot metal, which is at 200 degrees C at the beginning. Now, assuming that when we drop the 200 degrees C of a metal into the water, it does not produce any steam or lose any energy. The final temperature of the system, 22.4. So with the equation, we could calculate what is the Cx, the specific heat of the metal ingot. Now, in the discussion so far, we are focusing on the change of the temperature in the system that does not change its phase. But as in this example, it has actually hinted something. When you drop, for example, if you are not dropping the ingot of metal into water, you are dropping the water directly on the metal, you will see the water start to boil. If you just put drops of water onto the metal, you will see the water start to boil, and then it turns into steam. So there is a process which you are changing the phase of the material from one form into another, say from water into steam. This process, which we call the phase change, actually involves energy as well. So when you have the substance that is changing from solid into liquid or from liquid into the gas, these are phase change of a system. And during the phase change, a very important property is that no temperature change occurs. But even if there is no temperature change, it does not mean that heat energy is not required to change the phase. In fact, when you are melting the solid into liquid, you need to break some bondings or break some interactions between the atoms in order to make them mobile. Similarly, when you are turning the liquid into the gas, you need to provide additional energy for the liquid atoms to free from interactions among each other. So this would be the case of the gas systems. In the gas, you have atoms very far away from each other, unlike in the liquid. So they actually have additional energy. And this phase change would require additional energy. And the energy associated with the phase change is called latent heat. So the amount of the latent heat required for each mole of the amount of heat energy required for each unit mass of the system would be referred to as the latent heat of the system. Here, delta M refers to the mass change of the system when you are changing the system from one phase to the other. For example, some of the water may be boiling, but it does not boil completely. So only the part of the water that turns into steam would be considered for the latent heat. And because there are two possible forms of the phase change from solid to liquid or from liquid to gas, you have two different types of a latent heat. One type of it is the latent heat of, let me see, latent heat of fusion. And that refers to the phase change between liquid and solid. And the other type of a latent heat is the latent heat of vaporization. And that refers to the phase change between the liquid and the gas. So when the system, for example, is changing from the solid into liquid, it gains latent heat of fusion. On the other hand, if the system is converting from liquid back into solid, it loses latent heat of fusion. That is the general idea. So here you go. If the system enters the system, if the energy enters the system, the system either melts or vaporizes. And so the amount of a higher phase material would increase. Q should be positive. I don't know why delta M is referred to as negative at here. But let's put it this way. The Q that refers to the system should be positive. It must gain energy in order to move to become a higher phase material. On the other hand, if the energy is extracted from the system, it refers to the freezing or the condensation, and the material would be moving into more of the lower phase system, and the Q in this case would become negative. That is the general idea. So, for example, we have the case of melting the ice from very, very low temperature below its melting point. And eventually we bring it into steam. This would be the diagram that shows you the behavior. The x-axis refers to the amount of energy required, which may be provided, for example, by a constant power heater. Y-axis refers to the temperature of the whole system. At the beginning, for example, you have a beaker of ice at minus 30 degrees Celsius. So you put a heater to it. As the solid phase ice, it has a certain specific heat. So you are putting heat energy into the ice, and it comes to 0 degrees Celsius. So that is the beginning of the trace. At 0 degrees Celsius, if you keep on putting heat energy to the system, the ice will start to melt. So temperature does not change, but the phase of the system changes. It will gain energy due to the phase change until all the water is retrieved from the ice, until all the ice melts and becomes water. Then from 0 degrees Celsius, the water starts to increase in temperature until, again, 100 degrees Celsius. At this point, the water will start to turn into the steam. So the heat energy is gained by the water at the form of a latent heat of vaporization. So no temperature change, but you are changing the phase from the liquid form into the gas form, which is the steam. And finally, when all the water is converted into steam, eventually the steam could still be heated up to even higher temperatures. So that is the general idea for the phase change in the system. During the phase change, no temperature change occurs. In between them, when it is a constant single phase system, the temperature change can occur. So that is the general idea for putting the heat energy into a system. You have two different forms of heat energy addition or removal from the system. Either it changes the temperature of a single phase system, or it is removing or adding the heat energy to the system to change its phase without any change of the temperature. And here we have an example to show you what happens when the steam initially, well, when you are adding a steam into the water. So the steam is 130 degrees Celsius, and it is pumped into 200 grams of water, and it is put in a 100-gram glass container. So what is the situation? You have steam, and at the beginning you have the water in the glass. The steam at the beginning is 130 degrees Celsius, glass and the water at 20 degrees Celsius. When you pump the steam into the water, of course, the water increases the temperature. At the same time, the steam would lower its temperature from 130 degrees Celsius. So the temperature for the steam would be lowered from 130 degrees Celsius down to 100. And then it has a phase change to turn into water. And afterwards, it drops to finally 50 degrees C. That is the idea. So you are trying to consider the whole process in this example. So at the equation here, firstly, for the steam, you have the heat lost due to the lowering of temperature of the steam. Secondly, phase change from steam into water. Finally, the lowering of the temperature of the hot water from 100 degrees C to final temperature of 50 degrees C. That is the energy loss by the steam. And what about the temperature gain by the glass and the water? That is quite simple. MC delta T for the water as well as for the glass. So you put the two terms in the equation. So this is the Q hot and this is the Q cold. And in this way, you could calculate what is the mass of the steam required for the whole process. It looks very long, but the concept should be fairly straightforward. So it is the heat energy transfer, firstly, as the temperature change, and then you have the additional case for the steam for phase change. And of course, finally, when all the steam turns into water, it has the temperature change again in the single phase. So that is the idea. One of our classmates is asking, how can 200 grams of water be in a 100-gram container? Well, the 100-gram container can be very thin wall of glass, I presume. It's just like a paper cup that could be used for a very heavy mass of water. Okay, so I would stop at here, and on Thursday we would carry on with the discussion on the remaining part of the this chapter 20. Okay, so if you have any questions, you may stay behind, or we could discuss it in the consultation hour. Thank you.